Welcome to Web Handling. My name is Dave Roisum. This is a continuation of a mini-series on web machine design reviews. Here, we begin to check certain details that absolutely need, well, checking. That is, the size of the rollers. If we make our rollers too big, we cost the company more money due to extra metal and machining costs that provide no extra benefit. However, if we make our rollers too small, we cost the company even more money because now we risk additional waste, delay, and customer complaint due to a variety of problems that can arise from excessive deflection. We begin by gathering some must-know parameters that affect roller sizing. The most important of all is maximum product width. To this, we must add end allowances. For transport rollers, we need to accommodate routine path excursions, as well as perhaps a few of the less egregious upsets, such as might happen during a roll change or splice. For process rollers, we must take great care not to go too close to the ends with our product due to thermal gradients and the deflection-shaped nip details that we won't cover here. The working part of the roller's width needs to be quite carefully considered. Too wide and you increase machine costs. Too narrow and you increase the cost of waste and delay. Just right is, well, just right, and that depends on the details of your specific application. The next parameters affect forces and loads the rollers must withstand. This also must include the support type that greatly affects roller sizing, as well as framework design details. Many of these are detailed in my Mechanics of Rollers books, but you can see a brief summary and a couple points in my YouTube clips listed below. Once we have the required input parameters, we can then go on to sizing for deflection. As we covered in great detail in our Web 101 class, and even more detail in our roller book, the roller must withstand the forces of its own weight, tension, and nip for the case of process rollers. However, this is almost never a matter of strength. A roller strong enough to not break may be far too small to even run product. The roller must not bend excessively. We often use a Class B as a quality standard good enough for most processes and transport rollers alike. In our class and in the book, we listed several specific exceptions that may require upsizing the roll even more than deflection requires. Also, as we discussed, some of the applications might be better off with classes tighter or looser than B. However, the most important conceptual point comes from the physics of deflection. Since deflection goes as the inverse of the cube of roller diameter, that factor alone is much more important than shell wall thickness or shell material. Those factors are chosen after diameter, usually selected for reasons beyond deflection. Another point is one of common sense. That is, while each process roller is sized separately, because they are so super expensive, all transport rollers can probably be made of one nominal size, if it is sized for worst-case wrap angles. There is little reason to start from scratch on this bit of engineering because that has already been done and thoroughly field-proven for normal applications. The deflection calculation with worked-out examples is given in the roller book. However, you might find it faster and more reliable to use an Abbott app to do the calculation for you, rather than doing it by hand or making your own code or spreadsheet. Of course, some mature machine builders may already have their own internal code and standards along the lines of the roller book, so that may be a preferred route for them. As we mentioned earlier, there may be very specific reasons that rollers may need to be upsized beyond what the deflection criteria requires. To this, we need to add a check of the journals, this time for stresses, and for a very good reason: safety. While you never want the shell of a roller to deflect excessively, having a journal break is another level beyond of concern. While this topic of journals is super important, it is too lengthy to detail here. Suffice it to say that the designer must be expert in mechanics and metallurgy and risk analysis to keep the customer safe. That means they need to know the forces at each radius step of the journal and the stress concentration factor for each radius that can be found in design textbooks, and the fatigue endurance limit for that metal under those conditions that includes temperature and corrosion and other considerations. Finally, a generous safety factor needs to be added on all of this to keep failure rates so low that they are nearly absent, short of an unanticipated special cause accident that overloads the journals. Even those who are not tasked with such weighty details as safe design can still be on the alert. A pretty sure sign of an engineer who do not go to school is having bearing housings not nearly touching the heads of the rollers to keep the bending moments to a minimum. We do not want to move the bearings to the frame. We want to move the frame to the bearings. Since spindly journals with long stickouts are not uncommon in some converting machines, it is clear we cannot always assume that every designer went to school on roller design. The answer to who should check sizing is at least 2, if not 3, web handling trained engineers. The reason is that getting sizing wrong is at best costly, but could be debilitating or even unsafe. We should note that checking is like proofing a document. Yes, we should all proof our own work, but any writings going to the public should also be proofed by a typesetter and/or editor. In many cases, it is considered careless and perhaps even unethical to not have others review critical items, whether this is a publication or a design. The good news for roller sizing is that the process is really pretty simple when using apps for sizing deflection. Any of us should be able to double check that part anyway. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we will continue the design review process by taking an even deeper dive into roller details. This time we consider spans, wrap angles, and downweb tension profiles.